Welcome to the Deep Dive. Today, we're tackling a pretty big stack of research, really getting into this surprising connection between physics, math, and, well, music. We want to give you the shortcut to understanding this whole fascinating field.
It really is about bridging gaps, isn't it? We're looking at how these fundamental laws of the universe shape something we often think of as purely subjective, like beauty and sound. We're diving into the mathematics of music itself.
And our main guide for this is a true classic, Science and Music by Sir James Jeans. Now, you might know him as a giant of British cosmology. He was right there at the beginning, shaping how we understood stars.
Right, and he even suggested the steady-state theory back in the 20s. It's amazing that this same mind then turned to acoustics.
Exactly. And his book gives this incredibly clear account of everything from, how the ear physically works right through to the musical scale and even the acoustics of concert halls. It's quite the range.
It really is a simple yet precise guide.
So our mission today is, well, pretty straightforward. We want to unpack the hidden science, the principles that explain why some sounds just feel right, beautiful, ordered, and why others sound like noise, basically.
Yeah, why harmony works and dissonance jars.
By the end of this, you'll have a solid handle on the science that shapes every note you hear. Sound good?
Let's do it.
Okay, let's start simple, like really simple, the tuning fork. You strike it, and it produces what Jeans called a pure tone. What does that actually mean in physics terms?
It means the vibration is as clean as it gets. The prongs move back and forth in what's called simple harmonic motion. If you were to trace that movement over time, it draws a perfect sine curve. No complications, just that pure wave.
Simple harmonic motion.
Okay.
And that vibration, that sine wave, is what gives us pitch, right?
Precisely. Pitch is all about frequency. How many of those vibrations happen per second? More vibrations per second means a higher pitch. Fewer means lower.
And this is where we hit one of music's fundamental truths, something found just by experimenting, the octave.
Yes, the octave. Universally, it corresponds to an exact doubling of frequency. If you have a note at, say, 200 vibrations per second, the note exactly one octave higher is 400. Always that 2-to-1 ratio. It's foundational.
That's so clean mathematically, which makes the history of tuning standards seem, well, kind of chaotic. Jeans points out just how much disagreement there was.
Oh, it was wild. You look at the data he collected. In 1713, the organ at Strasbourg Cathedral tuned the note A to 393 vibrations per second.
Okay, 393.
But then, just a few decades earlier, an organ in Hamburg tuned A way up at 489 vibrations per second.
Right. 489 versus 393, that's huge. That's almost 4 semitones higher. Music written for one would sound completely different, maybe even unsingable on the other.
Exactly. Imagine trying to perform a piece written in Hamburg back in Strasbourg. It highlights why standardization became so crucial. Eventually, the international community agreed on A equals 440 vibrations per second. That's our modern standard.
Right, A440. We see that everywhere.
Yeah.
So once we locked that down, what was the next big mathematical hurdle for music, especially for instruments like the piano?
That standardization leads directly to the problem of temperament. We know the octave is a perfect 2.1 ratio. But musical scales, like the one on a piano, divide that octave into 12 smaller steps, semitones.
And you need those steps to be, well, equal, right? So you can play in different keys and have it sound consistent.
Exactly. You need to spread that doubling of frequency, that factor of 2, evenly across 12 steps. But you can't just divide the difference in frequency by 12. Since it's a ratio, you need to multiply by the same factor for each step.
Okay, so what's that magic multiplier?
It's the 12th root of 2, which comes out to approximately 1.05946. If you multiply a frequency by this number 12 times in a row,
You land exactly on double the original frequency, the octave.
precisely. It's this mathematical compromise, equal temperament, that makes modern keyed instruments work across all keys. Each interval is slightly imperfect compared to the pure ratios, but they're all equally imperfect, which is the key.
It's amazing. We start with that pure, simple sine wave from the tuning fork. But Jeeves himself said that sound is perfectly pure, but also perfectly uninteresting. Why is purity boring in music?
Because real instruments are much richer. Think of a violin or a piano. Their sound isn't just one pure sine wave, it's complex. It's made up of the main note, the fundamental, plus a whole series of additional pure tones blended in.
Those are the harmonics, or overtones.
That's right, harmonics. And for vibrating strings or columns of air, like in wind instruments, these harmonics have frequencies that are simple whole number multiples of the fundamental. So if the fundamental is frequency F, the harmonics are 2F, 3F, 4, and so on. The classic 1.2, 0.3, 0.4 ratio series.
And the specific mix of these harmonics is what makes a violin sound different from a flute, even playing the same note.
Exactly. That mix, the relative loudness of each harmonic, is what gives an instrument its timbre, its unique tone color or quality. The design of the instrument shapes this harmonic recipe.
Can you give an example? Like, how does the design affect the harmonics?
Sure, think about strings. When you bow a violin string, the bow kind of pulls and slips, creating a sawtooth vibration pattern. This excites all the harmonics quite strongly, giving the violin its very rich, bright, complex sound.
Okay, makes sense. But what about plucking a string, like on a guitar or a harp? That sounds different. Cleaner, maybe.
It is cleaner. When you pluck a string, especially near the middle, you don't excite the higher harmonics nearly as much. Jeans actually notes that for a plucked string, harmonics above the sixth contribute very little.
And why is that musically important?
Because it turns out the first six harmonics frequencies in the ratio 1.2, 0.3, 0.4, 0.5, 0.6 naturally form the notes of the basic major chord. By inherently suppressing those higher, potentially more dissonant harmonics, the plucked string sounds, as Jeans put it, almost entirely musical. It's a fortunate physical property.
Which loops back to what the ancient Greeks figured out, right? That notes sound good together consonant when their frequency ratios are simple whole numbers, like the perfect fifth, 3.2, or the major third, 5.4.
Exactly. Those simple ratios feel inherently stable and pleasing to the ear. It seems like a perfect mathematical system for music.
Seems perfect. But there's a catch, isn't there?
There's always a catch, yes. This elegant system hits a mathematical snag when you try to build a complete scale using those perfect intervals.
What's the clash? Where does the math break down?
It's this. If you tune 12 consecutive perfect fifths, each with that pure 3.2 ratio, you should theoretically end up back at the starting note, just 7 octaves higher.
Right. Okay, mathematically, that sounds logical.
Yeah.
A fifth is 7 semitones, 12 fifths is 84 semitones, which is 7 octaves.
Exactly. But when you actually calculate it, 12 steps of multiplying by 1.5, that's 3 divided by 2, doesn't quite equal 7 steps of multiplying by 2, the octave. The 12 fifths slightly overshoot the 7 octaves.
How much overshoot are we talking? Is it noticeable?
It's noticeable enough. The difference is a factor of about 1.0136, known as the comma of Pythagoras. It's roughly a quarter of a semitone.
A quarter of a semitone. So if you tuned a keyboard perfectly, using fifths, the last notes would sound jarringly out of tune with the first ones.
Horribly out of tune. That's why we need temperament. We have to compromise those perfect intervals slightly to make the whole system close the loop.
An equal temperament, that 12th root of 2 thing, is the modern compromise. Every interval is a tiny bit off, but it works in all keys. What about older systems? Did they try to keep some intervals perfect?
They did. Systems like mean tone temperament were designed to keep the major thirds absolutely pure, especially in the common keys like C major. And the fifths were pretty good too.
So what was the downside?
The downside was modulation. If you tried to play music in a key that was harmonically distant, like F sharp major or C sharp major, some intervals would become incredibly dissonant. So bad, in fact, they were called the wolf interval.
The wolf interval, because they sort of howled.
Presumably. It describes that really jarring, ugly sound you'd get. It shows the pain musicians went through before accepting the slightly out-of-tune everywhere nature of equal temperament.
It's fascinating how much math and compromise goes into just tuning the instrument.
Yeah.
But now let's shift to the listener. What happens when that sound, carefully tuned or not, actually reaches our ears? The human ear itself is, well, it's astonishing.
It really is. Jeans highlights its incredible sensitivity. First, the dynamic range is huge. We can handle sounds that vary in intensity by a factor of a trillion, basically. That's about 12 bells, or 120 decibels, from the threshold of hearing to the threshold of pain.
It's a trillion times difference in energy. But the physical sensitivity is even more mind-blowing, right?
That's the real shocker. How much does the air actually have to move to make the eardrum vibrate and register a sound?
Okay, hit me with it.
According to Jeans, the displacement can be less than a 10,000 millionth of an inch.
Wait, say that again? A 10,000 millionth.
Yes. It's an almost incomprehensibly small distance. To put it in perspective, that's about 1/100th the diameter of a single air molecule.
So our eardrum is detecting movements smaller than molecules. That's staggering.
It is. Our hearing operates right at the physical limits imposed by the random motion of air molecules themselves.
Yet, despite that sensitivity, our perception of loudness isn't straightforward. Double the sound energy doesn't mean double the perceived loudness.
Correct. That's related to the concept of the just noticeable difference, or JND. Our perception of loudness works more on ratios. to make a sound seem perceptibly louder.
You don't just add a fixed amount of energy.
No, you generally need to increase the energy by a certain proportion. Roughly speaking, you need about 25% more energy before the average person reliably says, yes, that's distinctly louder. It follows a logarithmic scale, not a linear one.
Okay, that makes sense. Now, here's the part that really surprised me in Gene's work. We think of the ear as just receiving sound, a microphone. But it's not passive, is it?
Not at all. This is maybe the most fascinating part. Because of the way the eardrum and the little bones behind it are structured, it's not perfectly symmetrical in how it responds to inward versus outward pressure.
Because of the bone structure, yeah.
Right. That asymmetry means the ear itself is a nonlinear system. It doesn't just pass the sound waves through unchanged. It actually creates new frequencies that weren't in the original sound.
Seriously. Our ears add notes. So if you play two loud notes together, say with frequencies P and Q,
the ear generates additional tones. The most prominent are the difference tone with a frequency of P minus Q and the summation tone with a frequency of P plus Q. Your own ear is producing these phantom notes internally.
That sounds like a weird biological glitch, but
Yeah.
you're saying it has a practical use, the acoustic based on organs.
Exactly. It's a brilliant piece of auditory engineering exploiting this glitch. Building really long organ pipes to produce super low bass notes like a 32-foot pipe for a 16 hertz fundamental is incredibly expensive and bulky. Plus, those very low frequencies are often hard to hear clearly anyway. So organ builders realized they could skip the giant 32-foot pipe. Instead, they used two smaller, cheaper pipes that play the second and third harmonics of that low note. For example, notes with frequencies 32 hertz and 48 hertz.
Okay, so they play those two higher notes.
And the listener's ear, because of that nonlinearity, hears those two frequencies, P48, Q32, and automatically generates the difference tone. 48 minus 32 equals 16 hertz.
So your brain fills in the missing fundamental. You perceive that deep 16 hertz bass note, even though the organ never physically produced it.
Precisely. The bass note resonates, quite literally, inside your head because your ear created it. It's an amazing acoustic trick.
Mind blown. Okay, so let's move outside the ear now to the final part of the journey. The room itself. Sound doesn't just travel directly from instrument to ear, especially not in a concert hall.
No, it bounces around, and every time sound energy transfers from one medium to another, like air vibrating a microphone diaphragm, or an electrical signal moving a speaker cone, or sound waves hitting your eardrum, there's potential for distortion. The quality changes slightly.
And in a concert hall, these changes get amplified because the sound reflects off walls, the ceiling, the floor, the audience. Hundreds of times, right?
Exactly. This brings us to the science of architectural acoustics, pioneered by people like W.C. Sabine at Harvard. He studied how different materials absorb sound, and crucially, absorption isn't uniform.
It depends on the material and the pitch.
Yes, different materials absorb high frequencies and low frequencies differently. Gene's gives an example. A wood block floor might reflect 97% of the energy of middle C.
Okay, very reflective for that pitch.
But for a note 4 octaves higher, a very high frequency, that same floor might only reflect 78% of the energy. It absorbs high pitches much more effectively than mid-range pitches.
So the room itself is filtering the sound based on frequency.
Absolutely. And that's why designing a good concert hall is so tricky. You need to achieve the right reverberation time, how long it takes for sound to fade away. Sabine calculated optimum times based on room size, maybe around 2.25 seconds for a very large hall.
But it's not just about the time. It's about the quality of that reverberation, right? The absorption needs to be balanced.
Critically important. If you line a room with materials that heavily absorb high frequencies, think thick carpets, heavy curtains, felt, canvas.
Things that make a room feel dead acoustically.
Exactly. If those materials soak up all the high-frequency energy, they're robbing the music of its timbre. Remember, timbre comes from the blend of harmonics, and the higher harmonics are crucial for brightness and character.
So if the room kills those high harmonics,
the consequences can be devastating for the music. Gene's puts it starkly. A priceless Stradivarius violin can end up sounding like a cheap violin. An oboe, known for its reedy, penetrating sound, can become dull, fat, and fluty.
wow. So the room's acoustics can literally strip away the identity of an instrument.
It steals its soul, essentially, by selectively silencing the very frequencies that define its unique voice. The room becomes part of the performance, for better or worse.
What an incredible journey. We started with the absolute mathematical purity of a sine wave from a tuning fork.
Moved through the complex but structured world of harmonics that give instruments their voice.
Encountered the unavoidable compromises needed to make our musical scales even work, like temperament.
Discovered the almost unbelievable sensitivity of the human ear.
And the even more amazing fact that our ears actually create tones that aren't even being played.
And finally, saw how the listening space itself actively shapes and filters the sound before it completes its journey. It truly highlights music as this interplay of physics, mathematics, biology, and even architecture.
It really does. And thinking about those compromises, like the Pythagorean comma and the need for temperament in our standard 12-note scale, it makes you wonder, doesn't it?
It definitely raises a provocative thought for the future.
Yeah.
We accept the slight imperfections of equal temperament because it's functional, but are we stuck with it forever?
Could music evolve beyond the 12-tone system?
Well, Jeans himself touched upon the mathematical possibilities. If you really wanted to achieve purer intervals, closer to those perfect small number ratios, you might need to abandon the 12-note octave entirely. There are theoretical systems using, say, 41 notes to the octave, or even 53.
53 notes in an octave, that sounds incredibly complex.
It would be, but it could offer far greater harmonic purity. So the question is, will the music of the future, in its constant search for new sounds and perhaps pure consonances, eventually break free from the 12-note compromise? Will our current system one day seem like a historical stepping stone, something for you to ponder?